In this theorem, we're going to prove if the limit as n goes to infinity of a sub n is equal to a, and the limit as n goes to an infinity of b sub n equals b, capital B, different from 0, and a and b are real numbers, and even the a sub n's and the b n's are real numbers, then the limit of the fraction or the quotient is the quotient of the limit. Now, in the proof, we want to show the following. And this is because I'm going to use the fact that the limit of a sub n times b sub n, and then goes to infinity, is equal to the limit of a sub n as n goes to infinity times the limit as n goes to infinity of b sub n. So what we want to show is we want to show that the limit as n goes to infinity of 1 over b sub n is 1 over b. This is what we want to show. But we're given the following. We're given that the limit as n goes to infinity of b sub n equals b. But that means the following. It means given any epsilon greater than 0, it does exist in n1 in the natural numbers such that whenever the little n's are sufficiently large, that is bigger than n, we have that bn minus b is less than epsilon. Okay, you pick the epsilon and we can find this capital N. So let us look at the difference that we want. We want to show this. Now for right now, and I did call this n sub 1, so let me call it n sub 1. Okay, for right now, we're only going to talk about n sub 1. N bigger than n sub 1. Now, 1 over b sub n minus 1 over b, this is equal to b sub n minus b in absolute value, divided by the absolute value of b sub n times the absolute value of b. Now we know that the top, the numerator, is less than epsilon. Because whenever the n's are bigger than n1, bn minus b in absolute value is less than epsilon, divided by the absolute value of b sub n times the absolute value of b. Now b is a constant and is positive. We know it's not 0. The absolute value of a non-zero number is going to be positive, and it's going to be constant. But b sub n is not constant. B sub n can change. Okay, b sub n could change. In fact, b sub n can even be 0. And what, I'm going to get this right this time. But now, what we want is to guarantee ourselves that b sub n is not 0. Since b is not 0, And B sub n is approaching, the B sub n's are approaching B closer and closer as n gets larger. There must exist an n2 such that whenever n is bigger than n2, the B sub n's are never zero. They're never zero. Okay. That's good for this. This is never undefined. So now, let us choose capital N to be the max of n1 and n2. We want this to be the max of n1 and n2. So now I can say two statements now. I can say this statement for any epsilon, and I can say this statement right here. Okay, so what we have is, if n is bigger than n, we have two things. B sub n minus b is still less than epsilon, and the B sub n's are not zero. That's what we have. Now, I need, so this is equal to, say, 1 over B sub n times epsilon over b. Now, this is fine. It's a constant. It's epsilon divided by a constant. But the 1 over B sub n, that's the problem. Since the limit as n goes to infinity of B sub n equals b, which is not 0, that implies that there exists an n3 such that if n is bigger than n3, let's actually write it, such that if n is bigger than n3, then we have that 1 over, well, we have that B sub n's are greater than, in absolute values, are greater than half for B. The absolute value of B over 2. Why? Because it's getting closer to B, not half of B. Now, we're talking about absolute value, so the absolute value of B is positive. If you're getting close to the absolute value of B at some point, I mean, right here is the absolute value of B. If that's, say, the n-axis, well then, right here would be half of B. If you're getting closer to B, the absolute value of B, at some point, you're going to be bigger than it. Well, this implies that 1 over B sub n will be less than 2 over the absolute value of B. So now we have it. Let us look closely at this. Since 1 over B sub n minus 1 over B is less than this here, 1 over absolute value of B sub n times epsilon over the absolute value of B. So this, we know that this is less than 2 over the absolute value of B times epsilon over the absolute value of B. This is 2 over the absolute value of b squared times epsilon. Now, I guess we have to be careful about the n's. Okay, now this is for n, little n being bigger than n3. For little n being bigger than n3. Well, let's fix that. Choose n prime to be the max of n and n3. So, for n greater than n prime, one over b sub n minus 1 over b in absolute value is less than 2 over absolute value of b squared times epsilon. Okay, so all we do is we choose a new epsilon to be the absolute value of b squared over 2 times epsilon. So just rewriting this line. So for n greater than n prime, 1 over bn minus 1 over b is less than 2 over the absolute value of b squared times the new epsilon, which is that. The absolute value of b squared over 2 times epsilon. But that's epsilon. The 2's cancel. The absolute values of b squared cancels. So this part is done. Hence, the limit as n goes to infinity of 1 over b sub n is 1 over b. Okay. But we didn't set out to prove that. We set out to prove that this limit is a over b. So now, the limit as n goes to infinity of a sub n over b sub n. Now I could have said this much earlier. Because a quotient can always be written as a product. And we know that the limit of a product, it's the limit of, in this case, a sub n times the limit as n goes to infinity of 1 over b sub n. That was true from the get-go. We just didn't know what this limit equaled. But now we do. We proved it. This first limit is a, and this second limit is a over b, and amazingly, when you multiply those, you get a over b. Theorem has been proved. I hope you liked the video. If you did, leave a nice comment. If you didn't, leave a bad comment. If you like proofs like these, subscribe to my channel. If you have a proof that you would like me to, or a theorem that you would like me to present the proof for, leave a comment. I'll read it, and most probably, I'll do the proof. Most of all, watch and learn.